Welcome to my talk, and thank you very much for such a nice introduction. And I'm Navid Hussain. I come from Karlsruhe Institute of Technology, KIT, and yeah, so I'll be presenting here direct writing of liquid metal microheaters for microwave applications. But as there are three different keywords: direct writing, liquid metals, and microheaters. But Professor Mazidi already said the high benchmark about writing liquid metals. But I'll still try to keep you interested. So why do we need liquid metal? So as we all know that in normal printed electronics, there are in terms of conductive metals, we use these nanoparticle based inks, and there we need post processing steps, and also sometimes the poor electrical conductivity, and also sometimes it is costly to fabricate these inks. So what is the solutions? I think liquid metals are the solutions. So as we see here in conventional nanoparticle based inks, we have the substrate, we print our pattern, and we post process it, usually heating it to some hundreds of degrees Celsius, or maybe sometimes photonic curing or other things. Then we have the conducting pattern. But in liquid metals, we can directly print it on the substrate, and we have the conducting pattern like this. So throughout this talk, when I'm mentioning liquid metals, I'm using this gallium stand. So it is also a gallium based liquid metal. As we say liquid metal, so it is the metal which is liquid in nature. So for gallium stand, melting point is around -19, and gallium stand is a mixture of 60%, 68% gallium, 22% indium, and 10% tin. So we know the ink, but there are certain problems with the writing of liquid metals. Some they have high surface tension, and also there is gallium oxide layer present on top of these liquid metals. So combination of all of these, it makes hard to be printed with inkjet systems or other printing direct writing methods. So we made this setup. So here we use glass capillaries. The typical ending is around 3 to 5 micrometers, and then we connect it with the plastic hose to a syringe pump. We put liquid metal gallium stand into the syringe, and we push it with the pump, and the liquid metal comes out of the tip of the glass capillary. The stage can go in X, Y, and Z directions, and with that, with the predefined pattern, we can print things, and everything can be monitored with the optical microscope. This is how the actual setup looks like. So this is the glass capillary connected to this syringe pump with the plastic hose. We put pressure here, and the liquid metal comes out of the glass capillary tip here. The stage can go in X, Y, and Z directions, and we can print different width of lines and everything. These are some, so this is the printing step. So once we know that this is the pattern we want to print, we define it, and then when we start it, the tips, the glass capillary stays static, and the stage moves, and it comes in contact with the tip, and then it moves in the directions what are needed, and we have our pattern there. These are some of the print results. Like you can print in centimeter scale, different width of the lines, very homogeneous lines, and also different structures like this, and also freestanding 3D lines for the connections. So now I come to microheater part. So we use this direct writing of liquid metals for fabrication of microheater structures. So we fabricated different designs and different architectures in microheater structures. We use these silver-based epoxy for contact pads, and monitor the temperature on the surface while applying a bias with this IR camera. But this is already defined in liquid metals being used for microheaters, that we have some problems like while heating. So let's as we see here on the left, this is freshly printed liquid metal lines, and after applying some bias and heating, we see that there is some kind of shrinkage, and also the line of width also shrinkage in height as well as in width. And if we see it under microscope in video, We see that why this is when the bias was applied on this liquid metal line. There is something going on in the liquid metal lines. So, and also after applying bias and when the liquid metal microheaters heats up to around more than 40, it becomes highly resistive, or as well as complete failure of the circuit. So that might be because of electromigration in liquid metal lines. So when we apply bias, the electro force generated with the moving of electrons on the liquid metal ions is more than maybe the force because of voltage applied in the electric field. And these liquid metal ions move on to the electrode side, and then we have just oxide layer standing like this. So like in this case, liquid metal moves on the sides and the oxide layer is remaining, and which makes it very highly resistive, sometimes just failure of the circuit. So possible solution is that we use a micro channel and then we put liquid metal on one side and keep the liquid metal flow into the circuit and keep on heating. But here again, there is again complexity, like fabricating micro fluidic channels and then constant supply for liquid metals and maybe wastage of liquid metal. With the direct writing, maybe if we found it like that when we increase as a possible solution, if we increase the heights on liquid metal lines, like just increasing the height of the liquid metal lines, it makes these structures more stable than the single lines, or it also reduces the complexity of other like other solutions. So after optimizing everything, here I present two of the samples. Like, so here both of the samples, PT sample 1 and 2, they were fabricated by printing lines. Like here 3 lines and here 5 lines on top of it, and the average width of the lines was around 109 micrometers. So for electrical characters, for temperature studies, like this sample 1 can reach up to 160 degrees, sample 2 can go up to 80 degrees, and for heating, we see that sample 1 can reach up to any stable condition and around 100 degrees in 200 seconds, and also sample 2 can reach around 80 degrees in 200 seconds, and both of them while cooling comes to near room temperature in 200 seconds. So then we use these microheater structures for microvalve applications, let's say, for a controlled mixing of 2 solvents or 2 materials. So here first we have this EBD microchannel sticky chip, and there is this microchannel on one side. So we block this microchannel with napalm, that is an hydrogel. So it has a critical temperature around 32 degrees from hydrated to non-hydrated state. So, and then we attach a glass slide at the back. One side, once it is blocked, we fill it with perovskite quantum dots just for fluorescent purposes under microscope, and another side with ethanol, we put a microheater structure on top of it, and everything is observed under fluorescent microscope. When we apply some bias on that, then initially it looks like that there is this napalm in between, and this quantum dots, fluorescent quantum dots are on one side and ethanol on the other side. So when we apply some bias, and when the microheater structure hits a substrate, and then the napalm, as it has a critical temperature of 32, it shrinks, and as it shrinks, both of them can move, and it looks like this after the shrinking. And so that we can say that we can see this controlled mixing of different materials or different solvents. So with that, I would like to conclude. So here in this talk, I show about capillary printing of liquid metal microheaters, and obviously it is easy fabrication. No post-processing steps are required, and I show here liquid metal microheaters for microwave applications. So with that, I would like to thank all of you for your kind attention, and obviously all of my colleagues, my collaborators, funding agencies, and for sure Flaps for providing me the opportunity to come here and present my work. Yeah, thank you once again.